Namaskar. Good afternoon to you all. Heartily, I welcome you to the INSA Distinguished Public Lecture on the topic of space missions for exploration and scientific goals, to be delivered by Secretary, Department of Space, Government of India, and Chairman, Indian Space Research Organization, Shri S. Somanath ji. I request Executive Director INSA, Dr. Brajesh Pandey, to kindly usher the distinguished dignitaries on the dais. Sir, please. Now I request all the dignitaries on the dais to please join in lighting the lamp ceremony. Sir, please. Thank you, everyone. Now I request at Kanpur Institute Chair Professor, former Secretary, Department of Science and Technology, Government of India, and President, Indian National Science Academy, Professor Ashutosh Sharma sir, to please deliver the introduction of the INSA Distinguished Public Lecture and welcome remarks. Sir.
Good afternoon. We are so very happy that we have Shri Somnath here with us to kickstart INSA's distinguished public lecture series. The idea for this particular lecture series, public lecture series, which requires no invitation, anybody is free to walk in. Of course, fortunately, only 250 people walked in, else we would have had problem. No, we wouldn't have had problem because I'm sure there's another room, which, if there's an overfill, that people can sit and watch on a big screen there. So that's fantastic. Let us welcome Shri Somnath with a very big, hand. So to here, like that, okay? It's such a proud moment for this auditorium and for everybody, all of us, to hear him. The great success of Chandrayaan. And we were just now discussing. See, people often think that the success of Chandrayaan is how to measure, temperature on the surface, which certainly is a big success, and how to land it properly. But even bigger success is the positivity and confidence that it generates in each one of us. And that actually is something that remains with people long after even maybe moon is gone. And so, how many people here have been inspired by the success of our mission on moon? A whole lot, just raise your hand. I mean, you celebrated, right? So this is what the success of that mission is. And I'm so glad that, it has this lasting imprint on our young and younger people and their confidence in our science and our scientists. Let me very quickly tell you. Oh, by the way, so we are in INSA. So I must do some self-promotion for 5 seconds or 8 seconds. Okay, so INSA was created in 1935 as a rather, club for the most distinguished scientists of the country. And there have been a lot of, the weaknesses in INSA are the same as the weaknesses in our general scientific ecosystem, which is the representation of women and young people participating in science, right? And so we are looking very hard, working very hard actually to address these problems in having a stakeholder base which is very diverse, which is very broad based, and so that everybody feels this happiness and this excitement of doing science and doing cutting edge science and being related, connected with our topmost scientists at every level. Okay, so now let me very briefly tell you the brief bio data of Shri Somnath ji, which is done require introduction. But anyhow, let me see. Shri Somnath is a distinguished scientist and secretary, Department of Space Chairman, Space Commission, and Chairman ISRO since 14 January 2022. Somnath ji is spanning a distinguished career of nearly 36 years, has made significant contributions in the area of space technology. This is the usual stuff they write in CV, by the way. But this is much beyond that. Okay, so I mean, everybody has made significant contributions, but there are only few who have landed the stuff on moon. So that's much better. And in the area of system engineering of launch vehicles. In his previous assignment as director, Vikram Sarabhai Space Center, the lead center of ISRO, he was responsible for launch vehicle technology. Under his leadership, the center achieved significant feats like crew escape system demonstration through pad aboard test. Nobody understood that, right? But anyway, it's a very very good thing to happen, and this is what makes it possible to land on the moon. Okay, so so on. So there are a whole lot of successes and the contributions that he has made to ISRO program. He's a fellow of Indian National Academy of Engineering, fellow of Aeronautical Society of India, Aeronautical Society of India, and a member of International Academy of Astronautics. He has published several papers in journals, seminars, area of structural dynamics, control dynamic analysis of separation mechanisms, vibration and acoustic testing, launch vehicle design, and launch services management. But this is not what actually I wanted to read you. Now, Pallav Bagla, the famous science journalist sitting here in green shirt in front. So first of all, let me acknowledge that it was his idea that we should have a public lecture series, and nobody better than Shri Somnath to kick-start that series, and we are doing that today. And every month there are going to be a follow-up of looking at the topical areas in science, cutting-edge areas, and something that inspires everybody. Public lectures. And the second thing that I want to tell you about Mr. Somnath is an interview that Pallav Bagla did recently, and it was very inspiring. So this is not just about temperature measurements. Okay, and let me repeat that. And so what I want to read about is among the points ISRO chairperson discussed were the many challenges he has faced over the course of his career, including the now not even believable comment. My position in ISRO was threatened. I could have been thrown out. So you see what happens. Oftentimes I see younger people, they know there's some adversity, and then they start losing hope. And they say, hey, world is not fair. Can I really do it? And all kind of negative things. You see, it happens in everybody's life. Make no mistakes about it. So today, who somebody who goes to moon, who lands some stuff there, it happens to the best of people. It also happens to the worst of people. But the whole point is that we cannot, give in to these depression or whatever that happens to us, but just move on along, and success would happen sooner or later. So don't think everything was nice for me in my life. I'm not saying this. He said that. I also face challenges in personal life and official life. You can be thrown out of an organization. Your position can be threatened. You are sometimes not even treated with great respect. I'm not even treated with any respect. Forget great respect. But anyway, be whatever it is. The whole point is that, that's what happens in everybody's life. And I want to emphasize that. You see, it's not our heroes are any different than each one of us. Each one of us has that potential to be that hero if we're not given to the negativity of life. Looking back on his career, India's top spaceman recalled harsh words ahead of an earlier launch. Many years ago, in launch of GSLV Mark III expedition, there was every possibility of a failure, but somebody had to take the decision of launching, and I took it. That could have been threatening because you see, you take risk, you fail, then you are in big trouble, isn't it? So I mean, isn't it better for me just to do, status quo? Just, that's how most people in this world live. But unless you take risk, that there is no big success that is ever possible. And so there's a great message here for our scientists to do profound research, take risk and fail. It's like, Hemingway said, it's better to have loved and lost than not to have loved at all. So, I mean, I don't know if it's Hemingway or somebody, but it totally reflects actually, this risk-taking ability. And so, so all that happens. And let me just read one last stuff from the interview that Pallav Bagla did. So, Mr. Somnath said, I had several limitations, both in terms of technical capabilities and my own personal capacity. You see, most of us actually don't even admit that. And so it is so good, when somebody say, look, each one of us have limitations, but to know what those limitations are and to overcome them, that is true hero's job. And a good scientist actually knows that. A dispassionate analysis, which is called Atmachintan, and not Atmachinta, but Atmachintan, which is positive, not negative. So you say, look, you work on this over a period of time in your own way. Very good. For me, my mental and physical growth as subject to knowledge growth was thanks to various people who came in my life at different times and gave me insight. Now, most people believe that if they are successful, it's because they are so capable. But if they fail, it's because of everybody else's failure. Right? You say, my boss didn't support, what happened, something happened, right? So this is fairly clear that this is, I mean, that's not the right way to think about it. So when one is successful, one gives ample credit to your team and your, people who actually worked around it, generations of it that work around it and make it all successful. So that's the hallmark of great leaders. And Mr. Somnath, I'm so happy to say, is one of such leader. And so I will conclude. Yeah. I said I'll conclude, but after three more sentences, you can clap again after that. So, okay. Now this is the punchline. Okay, here. So the concluding sentence, I was so impressed by it. We say we think of ourselves as so inferior today that we are not technologically advanced, not financially powerful, and we always think we are poor. We can't invest in all of this. I believe that this has to go for a nation which thinks that they are the one who are creators of knowledge. He said, emphasizing India can lead and will be a developed country soon. And I'm sure developed country both in terms of material success, but also we can lead in terms of that spiritual growth and progress, which is required for this planet to be around for next 500 years. Thank you very much, and thank you again.
Thank you so much, sir, for your amazing words. Now I request Professor Ashutosh Sharma, President INSA, to kindly felicitate our guest and speaker of today's lecture, Shri S. Somnath, with the token of appreciation on behalf of INSA.
Really, memento is given after the talk, but in this case, we are so sure I will give it to you for the talk.
Now I request Shri S. Somanath ji to kindly deliver his address. Sir.
Okay. Good evening, all of you. Thank you, Ashutosh ji, and all the distinguished people who are present here. And most importantly, the students who are here. My greetings to you. And to all those who are listening to the media, I believe that it's being streamed. And thank you for the nice words. And also for those small things that Palav Baglaji picked up from my interview. So you had a fortune to listen to that interview without actually reading it. So he lost quite a bit of readership through the today's program, or rather increased it. I do not know. In either way, it has been good to hear that, especially Sri Pallavaji, who has been chasing space for many years. And thank you for this opportunity to have the first of the public lecture series being inaugurated today or started today. And especially to speak about the space missions for exploration and scientific goals, what ISRO is trying to do. Because the work in space science has been way back. Even before we went to space, we started the space research through balloons. That's why I put a balloon on the left side. You don't need a rocket to do space research. You can just send the instrument hanging on the balloon. It will go up to say 40 kilometers up there. It can capture a lot of information. You can do sounding of the atmosphere, do measurements, and this is possible with the sounding rockets. Send them up to 50, 60, 100 kilometers. Send some instruments while it is coming down with the parachutes. You can measure. Then came the later objective of putting it in an orbit around Earth, then measure the parameters around that surface, or look at Earth as a remote sensing mission, or look beyond Earth into the space, vast or wilderness of the space, and do measurements. Later, move over to other planetary bodies and try to understand it. When remote sensing is just not enough, that you need to have in situ measurements, do missions like the Chandrayaan 2, Chandrayaan 3 as well. So what I want to talk about today is the type of work which we have done in the past. Also the work in Chandrayaan 3 specifically, because all of you may be interested to understand the Chandrayaan 3 in a little more detail. And the missions that we are planning for future exploration, and how you people can participate in such missions if you really want to. Students, you want to work on some development of sciences work, and then how ISRO can help you to work on, you create passion in science, scientific research, and expand this knowledge that we have today. So that's what I thought that I should quickly cover. I believe I have around 30-40 minutes. Okay, so I will start with our space era, which began long back. The first sounding rocket went in 1963 with a sodium vapor experiment. You know what for it is done? This, once you put it there, that it actually expands, it gives certain luminescence, and you can actually measure it. And over a period of time, it gives you certain characteristic of the upper atmosphere. Then the indigenous sounding rocket, the RH-75, just a 75 millimeter in diameter, launched with an altitude of just 7 kilometers. It went. Couldn't do much of science with this, but it's only showcased that we can launch a rocket. And all of this started at Tumba. The rocket launching started at Tumba, where there is supposed to be a magnetic equator passing nearby. It's not actually near Tumba, it's a little away. But still, okay, Tumba was a nice place for Sarabhai to set up the first of the rocket launch pad. And I started in a church there, still there. I go there many a times. This museum where we work. And the Tumba Equatorial Rocket Launching Station started primarily for conducting atmospheric research using rockets. Now, if you look at the space and planetary exploration, started way back in 60s, as I mentioned, the sounding rocket experiments, Sarabhai visioned the balloon-borne experiments. TIF, Tata Institute of Fundamental Research, is one of the leading agencies who have an ability to build huge balloons today. Even today, we make use of them. TIF facility at Hyderabad. Then we started the X-ray astronomy and cosmic ray studies. This was the area of research of Vikram Sarabhai. Then later, some of the scientists like U.R. Rao Kasturangan, many of them wanted to work in this area. X-ray astronomy started, upper atmosphere studies started. And the concept of scientific missions started at that time. Then ISRO started in 1969. The satellites which you built during 70s, the Aryabhatta, Bhaskara, the SROs, all of them were for scientific objective. They were not like the communication satellite, remote sensing satellite that we know today. There were some instruments like the X-ray astronomy satellites, aeronomy measurements, solar physics, gamma ray burst measurements, etc. So these were the type of payloads that was developed at that time to put in our satellites. And these satellites were not having precision orientation like what we have today. You cannot look at Earth very precisely. You cannot take images of that class because stabilized platforms were not there. Then it started the 2003, the solar X-ray spectrometer, which was studied in some of our satellites. The Chandrayaan 3 started in 2008. It was one of the major scientific satellite, which so to say, it looked at moon in much more detailed manner. The Gamma telescope, ray telescope for solar studies started. Then the YouthSat we sent, and then the Mars orbital mission came in 2013. And over the period, the rest of the satellites and Chandrayaan 3 came. So we can see today we have a great emphasis on scientific objectives from space. We try to build instruments. And these instruments are the key. You look at Chandrayaan mission, you all hail the landing on the moon. But after that landing, what? If you want to really understand moon, then you need to build instruments, very complex instruments there. For example, the instrument that is sitting on the Pragyan rover, it is a laser ablation spectrometer. You have to engineer it in such a small footprint. And there is another one is an alpha particle with the X-ray luminescence. You need to measure and identify the elemental composition. All done in a small packaging that is capable of remote operation. You can actually do it with the computers from here and get the data. And similarly, the instruments that are there on board the Chandrayaan lander also really fantastic instruments. I'll talk about some of them in Aditya L1, 7 instruments, very, very complex instruments. And all have to be done in 3 kilogram, 5 kilogram mass, which is autonomous and fantastic engineering pieces. I think if you are to really do space science, the capability of engineering complex instruments becomes very important. And the physical interpretation of the measurement in terms of the activity that are taking place is also very important. How to derive results out of the data, the measurements that you are getting, and how to be sure this measurement is actually giving the true picture of it. For example, you talked about temperature measurement of the lunar regolith. How good it is, whether it is really true or it is a false data. Now, you know that space-based scientific instruments, it also grew with our launch capability. Earlier, we were launching from Russia, the Aryabhatta, Bhaskara, the SRO started in ASLV. Then the PSLV started, we started putting small instruments on board some of the Earth observation satellites. With the Chandrayaan 1, which happened in PSLV, and later the GSLV Marg 3. Now we are sure about building heavier equipments and send it to space, like the Chandrayaan 3. So launch capability is equally important if you have to really do very useful science, significant science, and also very important. For example, the Aditya L1, I will tell you why Aditya L1 is very unique compared to many other satellites. It is simply because that we are able to put 7 instruments which are complementary in nature. If you really want to look at science, you can measure some parameters. But the secondary effects, the tertiary effects, if you are to measure on a complementary basis and then make sense out of the whole measurement, then you need to build large number of instruments which will observe the same phenomena at different spectral bands, different ways. Some looked at radiation, some look at particle part of it. So this becomes very an important issue. Let me talk about some of the important scientific missions like the Chandrayaan, Mars orbiter, Astrosat, and Chandrayaan 2. So Chandrayaan 1 was a mission which was conceived. At that time, we had only PSLV. We didn't even have the GSLV, which is a reliable rocket. The rocket was failing at that time, 2008, 2009 timeframe. And same with the Mars orbiter mission, when we did, the only rocket was PSLV. So the entire thing has to be engineered around the capability of the rocket. And it produced huge scientific outcome today. Chandrayaan 1 had a lot of instruments. I will explain that part. Similarly, the Mars orbital mission also produced huge amount of data. The Chandrayaan 1 lasted only 1 year. It was designed for 6 months life, but it lasted 1 year. But we are hoping that it will extend its life for longer, but it didn't happen. But look at Mars orbiter mission when it came, we designed it for 1 year life and it lasted for 8 years. And last year only we declared it non-functional. But today we have huge amount of data from Mars orbiter mission. publications from Chandrayaan 1 and Chandrayaan 2 are still coming out. Last week, there was a publication on the way in which the water is created on moon. It's a recent publication from US based on the Chandrayaan 1 data, which stopped functioning long back. Astrosat is again another very important satellite. Possibly many in this society, you may not be knowing about Astrosat in great detail, but Astrosat is very unique satellite which we built. It's a world-class satellite of the class of Chandra or the American observatories that we have put. It's a multispectral observatory which looks at universal creation of the universe in black holes, nebulas, the collision of stars, pulsars. It's capable of looking at gravitational waves, origin of the universe. Research on these topics are possible with Astrosat. It is still functioning. It was launched in 2015. And of course, Chandrayaan 2, we wanted to launch as a soft landing, which couldn't happen. But it's still orbiting moon and it is producing remote sensing data from the moon. Now, the Chandrayaan series is next one, Chandrayaan 1, Chandrayaan 2, and Chandrayaan 3. And you know that when we started Chandrayaan 1, we were not having a lot of instruments. The Indian ability to build instrument was very less. So we asked for some people to contribute to the mission. So we had a European contribution, we had United States contribution for various payloads. And of course, India also built through its Indian laboratories instruments on board. So all these instruments looked at the chemical, the mineralogical and photogeologic mapping of the whole of the moon in various spectral bands, visible, near infrared, low and high energy X-rays, and in a spectral and spatial resolution, which is very wide. People who looks at remote sensing data understand the significance of this terminology, which I mentioned here. In multiple bands, in various spectral and spatial resolution. It gives you so much of scientific outcome once you observe the same phenomena in multi-spectral band. And that's very important for to understand the physics of the problem. And Chandrayaan 2, again, when we started Chandrayaan 2, the capacity to build instruments slowly grew in our system. And various science labs in ISRO were able to build instruments. And so we didn't ask for any instruments to come from outside the country. And all the payloads on board Chandrayaan 2 and even Chandrayaan 3 are built by ISRO's laboratories or other science laboratories. So I will speak about the scientific instruments a little later. So Chandrayaan 2 and Chandrayaan 3 in terms of the scientific instruments were just the same with little bit of improvements here and there. In the Chandrayaan 1, when we are building the Chandrayaan 1, there was one person who intervened, and that is none other than Dr. APJ Abdul Kalam. When we presented this idea to him about the Chandrayaan 1, he was not in ISRO with ISRO at that time, but he said, if you are going to moon, you must make your footprint. You must put your flag on the moon. So how to do? The mission was already designed. The satellite was almost getting ready. The launch capacity was just enough. But Kalam, when he says something, we cannot say, no, sir, it's not possible. There is no possible answer to Abdul Kalam possible. So we immediately went back and designed one moon impact probe. It was a small cuboid of this much size. It has to be designed with its own cameras, scientific instruments, propulsion, etc. It was realized not by the satellite center. It was designed by the rocket center. In Vikrasara Space Center, we designed it. And because the main satellite was being built at the satellite center in Bangalore, and they were not ready to build something like this in less than 4 months. So some of us who are not experts in satellites started building MIP, the Moon Impact Probe. It contains solid propulsion rockets, unconventional in the satellite. And it had a spin rocket, which is again a solid, because it has to be injected into the surface and it has to be stabilized. So we created a rotating rockets, so the whole thing will move so that it doesn't turn. When you want to look at it, you need an inertial stability. So inertial stability can be given by spinning it. So you started spinning it. So spin rockets were made. Then we did a research. When you go to moon and fire solid rockets, it may not fire because you would have already chilled to a low temperature and the propellant may not catch fire. We have to make new propellant chemical composition to work in moon. We should not contaminate the cameras. So we looked at how to create propulsion which will not contaminate with the dust coming out of it. Should not contaminate cameras. So much of research did in just few months. We built the MIP and it was successfully deployed on the surface of the moon. And we still have the video of that actually moving towards the moon. But you can see the image rotating so fast. So we did the re-rotation and made it stable because computer can do all of that. And we made a stable image of the whole of the moon approaching it with the camera. And while it is moving, it did measurements along the path. And very good science came out of that simple instrument of moon impact. And all of you know that the Kalam's wish came to be a reality, that we had the first Indian-made object on the moon with the Chandrayaan 1 way back in 2008 itself. And you know that MIP actually went to the near to the South Pole, closer than the Chandrayaan 3 now. Chandrayaan 3 went out to 69 degree, whereas the MIP went up to 89 degree of the south. So the farthest item that went to the South Pole was actually in 2008 in Chandrayaan 1, not the Chandrayaan 3. Though we soft landed on moon in Chandrayaan 3, but the first impact took place much earlier. It also studied the latitudinal and altitudinal distribution of the lunar exosphere noble gases in just that course of impact time it did the measurements. Now, this is very interesting. See, if you look at the electromagnetic spectra, you can see the instruments which were put in Chandrayaan 1 was covering a wide band of that spectra. You can see how from radio to gamma ray, you were able to build instruments to look at it in various spectra. This is the crux of the problem of any in instrument development, sensor development in science. If you want to really make measurement out of the physical activity, the observation should be done, can be done only in electromagnetic spectrum, because when you are doing at a remote sensing, nothing else comes to you other than the radiation. So you need to look at in various spectra and then try to make physical sense of the measurement. So the hyperspectral imager, the miniature synthetic aperture radar, the infrared telescope, radiation dose monitoring, laser ranger, terrain mapping camera, X-ray sensors, gamma ray sensors, mineral identification through the gamma ray, high energy spectrometers. All these were designed, developed across the system. So we have a wide spectral observation in addition to the spatial distribution as well. So this is the most hailed finding of the Chandrayaan 1, the detection of the hydroxyl radical on the lunar surface, indicative of the future possibility of finding water. So the mapping of the Chandrayaan created a large map of possible concentration of water, which is more higher near to the pole, as we all expected. And this data is from the moon mineralogy mapper called M-Cube payload, which is a US payload. But then subsequently, the Indian observation also corroborated. Even Chandrayaan 2 also corroborated with this finding. So we have a good data about the water availability. Yet another scientific outcome out of Chandrayaan 2, Chandrayaan 1. This is about the interaction of the solar wind with the lunar surface. Possibly, you know what is a solar wind. It is solar wind are the coronal mass ejection and the particles that are traveling from sun all around the universe. And while it travels towards moon surface, it impacts with the magnetic sphere of the moon. You know, moon is not magnetic like Earth. It doesn't have a strong magnetic field, but it is still magnetic. It has lumps of magnetism here and there distributed, not like a, you know, Earth is a north-south pole. It is almost like a magnet. But if you look at moon, that magnet, it's not almost like a magnet. It has some area there is magnetism, some area there is no magnetism. So we do not know why it is so. Possibly that magma or the molten material inside is not there. It doesn't generate the current of the material flow, which actually creates a magnetic field on Earth. It's not present on the moon. And because of this, there is an interesting observation. When something orbits around moon, there is a funny orbit. It actually doesn't move around. When I say 100-kilometer orbit around moon, the satellite doesn't move at 100 kilometer. It actually moves like this. Sometime it comes closer to 70 kilometer, then it goes up to 100 kilometer. You can understand, no? The gravity distribution on moon is not symmetric. It is very wavy. Though physically it looks sphere, it is not gravitationally sphere. So when you calculate the orbit of the satellite around moon, it's not easy to calculate. You have to actually model the gravitational field mathematically with the higher order terms and then create the oscillatory motion of the satellite for us to, if you want to dock something, your calculation should be very precise. You have to capture that very well. So to understand the gravitational field, the magnetic field of a moon becomes very important for future moon missions. So here it shows how the solar winds interact with the magnetic field of moon and creates the neutral atoms. So this measurement was so crucial in one of the missions which we did in Chandrayaan 1. Here again, measurement of the ion concentration. This is also at different latitudes. This becomes very important because as one of the recent paper that came out, how water gets created, hydroxyl ions get created, and how the electron emissions happening from through the solar wind, the particle emissions are actually adding, creating neutral atoms and also creating elements on the surface. So this has been reasonably researched out of the finding of the Chandrayaan-1. Water vapor also. See, this is another interesting finding. One of the measurement was in detecting presence of water vapor in the faraway atmosphere of moon. You know, moon doesn't have an atmosphere. It's a very charged particle atmosphere, but still they were able to detect even presence of water molecules, even the outer surface of the faraway on the atmosphere on the moon. So the most important finding out of the Chandrayaan-1 was the understanding of moon changed drastically, and renewed interest in moon happened across the world. For example, moon is said to be a dry object. We understand that it is no longer a dry object. It is very active. Molecules are present. There is a lot of activity taking place. And they said geologically dead, but we understand it is still a dynamically and volcanically active. We recently put a sensor on looking at ILSA, which looks at the sensor vibration measurements. We found that there are activity taking place internal to the moon, which need to be understood. And we also said the regolith of the moon absorbs impinging solar winds protons, and this also found to be not correct. And similarly, the ion population, the solar influence is not there. We found the solar influence on the ion population. And also on the habitability of moon was addressed. And today we know that it is possible to live on the moon, especially under cover of some of the buried areas, etc. Or if you find caves, you can actually live safely on moon surface. Of course, you can't live on the outer surface of the moon at all. You know why? Why can't you live on the surface of the moon? If you build a house and stay there, is it possible? No. Because anytime you will be hit by a meteor. See on Earth, how many meteors hit per every day? Lakhs of them. Earth is bombarded with meteors. Lakhs of meteors come and hit the Earth's surface, but we are not hit by any that easily because the atmosphere protects you from that object ever reaching the ground. It burns up in the atmosphere. In the absence of atmosphere, all that lakhs of meteor showers will be felt on your top. So if an astronaut moves around the moon surface, he can be hit by a meteor at any point in time. So this is the grave danger of living on planets without atmosphere. So moon is not that easy to live unless you have a protection against meteoritic attack. For example, Chandrayaan-3 is now sitting on the moon. No? Last 14 days. I'm sure it is not hit by any meteor yet. That's why it is not waking up. Huh? Okay, the sharpest ever image on the moon came out of the OHRC, the Orbital High Resolution Camera on Chandrayaan-2. Today I have picture of moon in 25 centimeter resolution, which is one of the best ever image that has come out of any moon mission so far. There, of course, American observation cameras also gives you similar resolution, which originally before Chandrayaan-2 we purchased some area from them for use in our mission. Today we have our own images, and this image has actually gone into Chandrayaan-3 planning, and the landing area has been earmarked, identified using the Chandrayaan-2 image, which is a high resolution image. And we understood the Chandrayaan better with moon better with Chandrayaan-2 as well. For example, the presence of argon, lunar surface composition by the X-ray diffraction instruments, the lunar hydration features, finding out sodium abundance on the moon surface. Of course, sodium abundance is very important to look at the similarity of Earth with the moon, whether moon is a byproduct of the Earth through some collision, some part came out of Earth and then went and created the moon. We do not know. So there are many theories like that. And this can be created only by the similarity of mineralogical composition between Earth and moon. So that finding is important. So in summary, if Chandrayaan-1 and Chandrayaan-2 compare, we find that there are a lot of similarities in findings from Chandrayaan-1 to Chandrayaan-2, but we lost the Chandrayaan-2 landing, which prevented from getting that knowledge much earlier than Chandrayaan-3. I am sure Chandrayaan-3 will replenish some of those lost goals of Chandrayaan-2. So I am not going to read all of this. Now coming to Chandrayaan-3 and the lander, the rover, which has made a classical impact. You can see the rocket, the lad launched, and I am so passionate about this, the leftmost side, because without the rocket, Chandrayaan-3 and 2 were not there. We have 4-ton plus capability to put in orbit now. huge satellites can be built and launched inside the payload fairing, which is almost 5 meters in diameter. Just imagine what is 5 meters in diameter. It will be much bigger than this. Okay, so the space in where I put the satellite is a huge area, and that's why we are able to launch such big satellites. And overall, Chandrayaan 3 was similar to Chandrayaan 2, but with a goal of soft landing and do the scientific missions. And a lot of re-engineering in the Chandrayaan 3 happened post Chandrayaan 2 failure to land. And here we maintained the overall mass, but we shifted a lot of mass from the orbiter to lander and created a very better design of lander so as to create the experiments and success that we have seen now. One of the important accomplishment in the Chandrayaan 2 was that, of course, it's a soft landing, and it is a result of very conscious decisions that we took on the way. One of them, I don't want to tell all such decisions that led to the success, but one of the important decisions that we took, that the landing area is no longer going to be very small. In Chandrayaan 2, we put only half a kilometer by half a kilometer area is targeted as the landing area. Now we said that it will be 4 kilometer by 2.5 kilometer because we have a high resolution image of moon today, and I can land anywhere of this area, provided it doesn't get into any of those holes that you see, So the intelligence should be there on the camera to not to land on either boulders or craters. You should identify a good area within that 4 kilometer by 2.5 kilometer. I should land at the center of the centroid of the area. So, and this is a track by which it flies on top, and so that when it lands from 30 kilometers to the landing site, we will be targeting the ideal location. And if the ideal location is not going to be met due to whatever may be the reason, but it will still come and land anywhere within this area safely. So this made sure my algorithms are safer. It doesn't get into problems that we saw in the Chandrayaan 2. So it was a very strategic decision to do this. But the most important thing that led to the success is the rigor of testing. I think this I want to tell you in space missions. Unfortunately, we are not able to simulate the conditions of the moon on ground. You know why it is not possible? Why moon's condition cannot be simulated on Earth? First and foremost is the gravity. The gravity is only 1/6. So if anything you take, it will weigh 1/6 on the moon. And whereas the engine, when it fires, it produces the same thrust. Thrust is not a function of the gravity. So the reactions, so the balance of forces, which you cannot simulate there. Second is atmosphere. The atmosphere is always present here. I cannot get rid of an atmosphere and produce vacuum and then do all these tests there. I cannot create a huge facility where there is vacuum. So that cannot be done properly. And the variation of the gravity, which I mentioned about the moon, cannot be created because it is moving at tremendous speeds. The satellite, which is moving at this on the orbit, it has a speed of 1,670 meters per second, almost 1.6 kilometers per second. So from that speed, I have to reduce the speed to 0 kilometers per second when it has to land. And how to simulate it on Earth? The fastest aircraft on Earth will travel only at very low speeds, like 500, 600 kilometers per hour. So there is no way to simulate this type of speeds and then recreate the trajectory that actually it will take. So it has to be done only on computer. And you have to also create the impact conditions. You have to multi-sensors are there. There are radar altimeters, there are laser altimeters, there are optical sensors, which actually take pictures when things are moving very, very fast. And it has to sense that image and makes the coordinates measured from those pictures. How can we do from static conditions? If you do and dynamic conditions, the images will be different. And at speeds, it will also make difference in its interpretation capability. But all these are challenges. So we did at speeds which are moderate enough to do with helicopters, and gravity compensation by crane and countermass measured. So some engineering solutions were worked out to find out how to do this test on simulated test beds. And this test gave us huge amount of confidence to do the experiment on moon. And you can understand the landing on the moon is never ever simulated in reality before it actually lands. So this is the whole problem with the rocket's work. Every rocket, when we build and launch, it has not flown before. It's going to fly for the very first launch for the very first time in the integrated manner. Think of an aircraft design. An aircraft, when you are designing and building and launching for its commercial operations, first it will do taxiing. That taxiing will be done for some 1 month. After that, it will take off to some 10 kilometers. Then it will come back and land. Then go slowly. It will raise its operational margin slowly until it actually flies its full domain of capability. For rocket, it's not possible. The very first flight should be at its fullest capability. There is nothing compromising on it possible. So the design of a rocket is very unpardoning to anybody. it operates at its threshold in the very first flight. There is no opportunity. So when you hear about the first mission failure, you should understand that it has not flown before. That's why it has flown in the first flight, failed in the first flight, unlike many others. So I tell those who are designing cars are fantastic engineering pieces, no? But it has hundreds of times of operational flexibility to re-engineer when you find a problem. If you encounter a problem in a car, the best thing you can do is what? Switch off the engine, park nearby, and call the workshop. But I don't have any capability to do that in space missions. I can't park the rocket anywhere and ask for help. So everything should work on board successfully, and thousands of elements have to work in synchronization measurements so as to make anything successful. That's why the power descent phase raised so much of curiosity everywhere. Something which is moving at 1,600 plus meters per second speed has to come and land, and that's velocity is horizontal, and I have to kill all the velocity. The rigid body dynamics, those how to calculate dynamical motion of objects, you will understand something moving at horizontal velocity. Once you kill all the horizontal velocity, it will fall like a rock. Gravity will take over and it will pick up the velocity. So it will fall. So I cannot kill the horizontal velocity. I have to kill the horizontal velocity in a controlled manner and allow gravity to take its and then create vertical velocity so that, and vertical velocity will peak. The moment I kill horizontal velocity, vertical velocity will start rising. And I have to control the vertical velocity so that ultimately I should get zero velocity. So it's a very interesting phenomenon. It starts from zero vertical velocity, end in zero vertical velocity. Between them, the vertical velocity will go up and down. And the whole of this is done in an optimal algorithm. Optimality, control optimality, optimal solutions to complex mathematical problem. It's a very complex optimization problem. Those who understand mathematics, you can say that how to optimize the trajectory from one point to another while minimizing time, minimizing fuel consumption, minimizing load, minimizing uncertainty and parameter perturbation. It's a very complex mathematical problem of solving, moving from one point to another. And this has to be done on board computer, and computer has to find out how to do this. And we put algorithms. And if you encounter boundary exceedance of any parameters, it should take alternate paths. So we design alternate paths, look at how every instant how things are changing. If some sensor data is not coming, how to take some other sensor data. So sensor fusion comes in, identification of failures and corrective actions come in. So it's a complex algorithm working inside with about 5-6 instruments which actually feeds into it: cameras, accelerometers, gyroscopes, lasers, radar altimeters, all feeding into the system. So much information coming, it has to synthesize and make those decisions while it travels. This is a complex problem of software, sensor, control, fusion. I think most of that work in this Chandrayaan landing has been spent on it. You would have heard of something called guidance algorithm. Guidance is precisely this: how to move one object from one point A to one point B while controlling optimizing the trajectory to meet all those control parameters. This is a mathematical problem. We have worked with the professors in IISc. Our young engineers have solved this problem beautifully this time. And more than that, it has also created history by the last time we had a failure and we found out why it failed without collecting any debris from moon. You understand what I said? If you have a crash somewhere, you can always collect the debris and understand what has gone wrong, whether brake failure occurred or hydraulic fuel leaked. But when the failure occurs on moon, what will you do? I cannot send another machine there to collect the debris. The only option I have is to work on the mathematical model and find out what could have gone wrong. I think that has been done very well. That's why we were able to achieve success this time. Now coming to science goals and instruments, I talked about some of the science instruments on board. The CHASTE, which is the Chandra Surface Thermophysical Experiment. It's an instrument in which we pierce a sensor into the surface, and it's a composite material. Inside there are thermocouples, sensors, RTD temperature gauges, etc. It heats up and then measure the temperature variations along this. This will give you some picture about the lunar regolith thermophysical characteristic like the conductivity, the specific heat, etc. So this is one of the experiment. Rambha LP is a Langmuir probe, which is a spherical probe, which you extend outward and measure, give a potential to it, and you can measure the charged particles density on the surface of the moon, not on the surface of the moon, in the vicinity of the surface. ILSA is an instrument for lunar seismic activity. It is nothing but an accelerometer, very precise accelerometer using MEMS device in 3 axis, which actually measures the vibration happening on the surface of the moon. And LRA is a laser reflector array, which is a passive array, which is mounted on the corner of the Chandrayaan, which if you send a laser beam, you can get a reflection. and you can actually identify its position. So these were the payloads on the lander. And on the rover, we had two payloads, the LIPS and APS-XS. And the first instrument is a laser-induced breakdown spectroscope. You send a diode laser focused on the surface of the moon. And when it hits there, it ablates the material, and the ablation is spectroscopically analyzed and looks for the elemental composition. And this is mapped against a lot of experiments we did on the laboratory. And we are able to find out very clear signatures of the elemental composition as marked here. And APXS is an alpha particle X-ray spectrometer where you send alpha radiations. It's actually from a radioactive source from our atomic Department of Atomic Energy provided us that alpha sources, which you put on inside. And that alpha is ejected, focused on the surface, and this gives X-ray luminescence on the composition, and you can actually measure the elemental composition. SHAPE is a payload which is put on, is called spectropolarimetry of habitable planet Earth, which is mounted on the orbiter, which looks at Earth and then look for some polarimetric spectral characteristic of the Earth, so as to find that if you find any other planet of similar to a exosolar planet, whether the spectral characteristic can be similar, so that you can say the life gives out this spectral characteristic. The presence of life on Earth gives out this spectral characteristic. It's too much to believe that the life on any other planet will be similar to Earth. I don't think it will be similar to Earth, but still it gives you some understanding of how in the near infrared region, whether the radiation that are coming from Earth could be used for such measurements. So I'm just quickly showing you some of the instruments that we built. The ILSA is a very compact payload with its MEMS-based sensors developed internally, and it measures the acceleromission. The Chaste, which I mentioned, is a compact probe of composites, which is temperature sensors, and it also has a drive mechanism. So it's screw drive. It actually projects, and you can motorize and drive it into the surface and take it out also. So we have done it 2 times. Of course, this development took many years. You will understand this term, the composite material development, its strength, its ability to pierce, the characterization of it took many years to make it. And this is done at Vikram Sarabhai Space Center. The REMBA payload is also a very classical measurement, which you have been doing within many spacecraft. And this looks at the lunar ionospheric electron temperature and plasma density. We have been regularly using it for measurements or using sounding rockets and satellites. So it did exceedingly good measurements. And we found that the electron density, which you assumed on the moon surface, is actually found to be lower than current knowledge. The alpha particle X-ray spectrometer, you can see it marked on the rover. It is actually folded and kept, and there is an actuator to bring it down, and then it measures it. So you can see the compactness of this. The whole of the rover is very small. It's a small toy car like, and on that you are able to mount such a device and do the spectral measurements. And on the left side you see the Curium 244 source, which is mounted on it as an alpha emitter, and then the central detector, which actually measures the X-ray from the objects on which it is illuminated. And the laser-induced breakdown spectrometer on the rover, the details which I am giving here. So it's a pulse laser with a focusing unit, and the optics, everything is built by us. And all of this is done within the ISRO facilities. We have an optical development team at Laboratory for Electro-Optic Systems, and they built all of this payload. And the spectropolarimetry of habitable space Earth is built by a satellite center, which has some good experience of building polarimetric experiments in space. I'm not going to explain all the elements of this. The only thing which I want to tell you is that it's a very compact 3 kilogram, 5 kilogram mass only, this instruments, and it is able to produce so much of outcome out of it. So the whole crux of the space exploration is how to build very valuable instruments within very compact footprint. Detectors, the compact electronics, mass optimization, power optimization becomes very important. It's very easy to build huge instruments. For example, a spectroscope you want to build in a 10 kilogram, 20 kilogram footprint is very easy because technology allows you. But if you have to do it in 2 kilogram, it becomes a big challenge. Now let me move on from Chandrayaan to Mars orbiter mission, which was launched in 2013. And the best Mars image came out of the Mars orbiter mission. So here the issue was look at the planetology of the Mars, its habitability, and its evolution. These 3 things we wanted to study, launched. And you can look at the images. I'm not going to speak much about the the findings, but look at the atmosphere. You know, Mars, why Mars is so interesting? I think many of you students may be knowing, because Mars is having mass almost equal to that of Earth. Its gravity is almost similar. Its period of rotation is almost 24 hours. Day and night is similar to that of Earth. But only problem is that it has a very thin atmosphere, very, very thin. And it is dominated by carbon dioxide, so you can't go and live there. But a lot of research has happened that tomorrow, possibly Mars will become habitable if you work on it, terraforming if you do, and if you do many things. Like the way Earth evolved over a period of time to become habitable could be done for Mars as well. So a lot of insights on the Martian atmosphere came out of the MOM. Look at in various ways the study was done, looking at the argon presence, how the atmosphere is so thin. So if you have a gravity field which is more or less closer to Earth, why the atmosphere on Mars vanished? Nobody knows. And the question is that why the atmosphere on Earth is still not vanished. Tomorrow will it become thinner? And so that none of us could live here? How the atmosphere is escaping out of this, due to what interactions this is happening? We need to address this. I think the evolution of the habitable planets is a very important topic that need to be researched. Of course, a lot of photos came out of Mars orbiter mission. One of them is imaging of the Phobos and Deimos of the by the planets of the Mars while Mars MOM was moving around. Also, the effect of the dust storm events captured beautifully by the Mars orbiter mission payload, like the MENCA, MAVEN, etc. MAVEN is American payload. The albedo measurements on the surface of the Mars, which is nothing but what is albedo is the emitted radiations which are measured from the surface of the Mars. Beautiful pictures. And look at this picture. It's a three-dimensional picture of the Mars. It has been created using the images that we have collected. Such a beautiful image of three-dimensional picture has never been done before of the Mars. So a lot of achievements out of this Mars orbiter mission, which was completed 6 months on 2015, but now it is declared defunct, and a lot of research publications have come out of it. I'm not going to describe it. One of the interesting study that we did with Mars, which was not originally understood, is a radio occultation experiment. That is, when Earth and Mars were like this in this orientation, the signal from the Mars orbital mission was going through the coronal field of Sun. We could do some very interesting experiment through solar corona. So it gives you to understand the coronal dynamics. So by a radio wave traveling through the corona, you can actually study the corona. So many new such studies were done using Mars orbiter mission. Astrosat is again another interesting experiment, which is a multi-wavelength observatory of in space with so much of instruments like the ultraviolet imaging telescope, soft X-ray telescope, large area X-ray proportional counter with the CSRTA technology, a scanning sky monitor, with the contribution from various institutions, ISRO, TIFR, PRL, Raman Research Institute, and many others built these instruments on board Astrosat. And there is a huge science pool who is actually making use of this data. And this data is put in our data center, which I will tell you later how to, even if you people want to access this data and do research, it is available to you. So science highlight from Astrosat includes many things. For example, the puzzle of the red hot star, pulse, off-pulse X-ray polarization from Crab Nebula, pulsar, for example, not nebula, pulsar, emission from Butterfly Nebula, discovery of Lyman continuum, discovery of intermediate state in this particular object. Like this, many science observations from the universe came out of Astrosat, and still it is continuing. So it looks at the black holes, it looks at multi-level observations of pulsars, neutron stars, binaries, etc. So one of the important picture that came out during that time, the comparing the galaxy image versus the Astrosat image, the clarity that has come, which is very good, comparing with the NASA instrument. Now I will talk about the Aditya L1 mission. Aditya L1 mission is just launched, and it is on the way to the Lagrangian point. And after, you can see the orbit around Earth, which is shown by the elliptical orbits, and it will travel next 90+ days to reach the halo orbit around L1. I think all of you know what is L1. I think I don't have to explain what is L1. L1 is the point which is between two objects, the Earth and the Sun, where the gravity becomes neutralized. But L1 is not a fixed point. It has influence from moon, it has influence from planets and other bodies. So anything that put around L1 will be subjected to three-dimensional motion, and we call it halo orbit. And the orbit of this Aditya L1 will be a very huge one in which the object will continue to move around this in large periodicity, and to look at sun continuously and also maintain contact with Earth continuously. So you can actually observe sun and get the data on a 24-hour basis. This is advantage. And we will not always position this satellite directly along the line of sight. We will put the satellite such a way that it looks at sun, it doesn't obstruct the sun. Because sun has a very high amount of electromagnetic radiation. If anything is put along the sun, you put a radar pickup and then try to pick up, you get only noise. You cannot actually see anything exactly come along the line of sun. You cannot communicate with it because sun is such a strong electromagnetic emitter. So you have to put it slightly shifted sideways so it doesn't come in the way of communication. So that's why the L1 and the halo orbit comes in. I believe you understood what I said. Now, there are a lot of instruments that are coming as part of it. There are 7 instruments on board the Aditya L1. The most important instrument is called the Visible Emission Line Coronagraph, which is developed by Indian Institute of Astrophysics. The Ultraviolet Imaging Telescope, which is done by the IUCA Inter-University Center for Astronomy and Astrophysics. The other remaining payloads like the X-ray, soft X-ray, hard X-ray, spectrometers, the plasma analyzer packages, the magnetic sensors, all developed within ISRO. So the point here is that the sun is being observed using multiple sensors. It crosses the disk of the sun and it looks at the corona and how coronal mass ejection takes place, the events, the modeling of the corona. And when a coronal ejection happens, it gives out X-rays of various nature. So that sense that radiation is measured. It also gives us particles, and we measure the particle using the plasma analyzer. It also changes the magnetic field in the interstellar space between sun and Earth and measures the magnetic field. So we get a correlated measurement. And this is the interesting part of the instrument. So this is a new satellite which is just ready. It is fully built and kept in ready for launch, but most probably will launch it only by December. It's called X-ray polarimeter satellite. So this is meant to study bright X-ray pulsars. You know what exactly it is? X-ray pulsars are the stars which are dead now in the process of death, and this gives out X-rays, a burst of X-rays. And if you study it in polarimetric way, you can actually look at it as materials where the material which is drawn from nearby stars. For example, black hole attract material to be taken from nearby stars, and it generates huge amount of X-ray radiation. And if you study that, you can look at how black holes eat into other stars. So 2 such payloads are there. One is called POLIX, which is a polarimeter instrument in X-ray, and XPEX, which is an X-ray spectrometer in 2 different energy bands. And this will observe such pulsars and study deeply. And this is a very small satellite, so just 450 kilogram satellite, which is very unique scientific instrument. And we have a lot of missions in the conceptual phase. We want to do mission to Venus, which is already configured. The payloads are already developed. You know, Venus is very interesting planet again. It also has atmosphere. Here the issue is that atmosphere is so thick. The atmospheric pressure on Venus, very near to the surface, is approximately 100 times that of Earth. We don't know why it is so thick. And it is full of acids. And you cannot even penetrate the surface. And the top of the atmosphere is full of clouds. You can see that there are images taken on the surface of it. And we do not know whether there is a hard surface on the Venus yet. So a lot of scientific research has come how to go to Venus, how to float using balloons on top and do research, how to pierce into the surface and understand the Venus. Why we are trying to understand all of this? Because Earth could be one day Venus. I don't know. Maybe we have 10,000 years later, we may slowly, progressively change our characteristic, because Earth was never like this. Earth was not a habitable place long back. You know what is the life of Earth? And we are only at the fag end of very small part of the life of Earth only that human beings are there. But much of his life was not habitable at all. So it is important for us to understand the evolution of planetary bodies. And only if you look at Venus, Mars, etc., that you can actually study and what effects are there in your activity that are taking place in the Earth that actually changes Earth and make it habitable or non-habitable or surviving or non-surviving. All this will depend on your understanding of it and your ability to act on it. We also work on aeronomy satellites, which is called Disha. There are 2 satellites which will be putting to understand the aeronomy of the. This is basically looking at the outer space climate, which actually affects the closer behavior of this Earth climate. So here we are looking at various magnetic fields that are happening, the solar data that is coming to, solar winds that are coming to it, how it is concentrating on poles, and how that particles are getting, the emissions which are taking place on the poles. All these are looked at by the Disha satellites. We are also conceiving a satellite called ExoWorlds. ExoWorld is a mission for looking at exosolar planets. I hope you know about exosolar planets. Exosolar planets are the planets which are around other stars, not sun. And we have already found out how many exosolar planets till now. We means the whole of the observing countries. Almost 5,000 of exosolar planets have already been discovered by various observatories, both ground-based as well as space-based. And it is 5,000. It is heard that at least hundreds of them are closer to similar to Earth, habitable possibly by the temperature, distance, gravity, etc. And many of them have atmospheres. And if you can understand the atmosphere, then we get an idea whether some of these exosolar planets are livable, human beings can migrate. But we still do not know how to travel and reach up to that. To travel from here to reach up to that will take a few generations. I don't know how many generations. But still, it is important to study of them. And this can be studied by a very interesting method, that when the radiation from the star goes through the atmosphere, it gets modified. And you can actually look at the spectral characteristic of this modification, this radiation coming through the atmosphere, and you can understand what the atmosphere is created out of. So this is the goal of the ExoWorld satellite. We also work with many global agencies like with the Japanese, with the French, and we have been working with the US in the past, and this continued to remain as our engagement. For example, we work with NASA. NASA, ISRO synthetic aperture radar and 2-band is a very important payload we are working. We also have a lunar mission currently going on with Japan, in which the lander, they will provide you the rover, will provide a big rover, and we have to make a lander, and we will launch it in their rocket. This is a plan yet to be approved, but I am telling you, these are work in progress, not really approved programs. So don't report that I have said that there is immediately launch. We also provide young people an opportunity to conduct science experiments using our upper stages of rocket. PS4 we call it. The 4th stage of the PSLV after its mission is in the orbit. It's like a satellite there. It doesn't come down. So what we have done is we are equipped it with the solar panels, we are equipped with the batteries, we are equipped with the transmitters. So if you have an instrument developed in any of your universities, laboratories, I am very happy to host it and conduct the measurements from space and give you the data free. You don't have to do rest of that. You don't have to make it into satellite. You just do the science instrument development. Rest of that we will take care. And most probably it will be done free of cost to you, because we are supposed to encourage you people to do it. So I want to tell you the PSLV is currently available yearly 2 or 3 times. We provide you this capability. If you come with a proposal from universities and research establishment, we'll be happy to onboard. And many people are doing it. I think many startups have already done it. Some of them have developed the capability. Some of them have grown to become satellite developers. So it's a very interesting thing happening. We also have Gaganyaan program, human spaceflight program. This also gives you a lot of opportunity for scientific goals and scientific research, like medical and biotechnological research, chemical and polymeric synthesis, additive manufacturing research, as well as materials, endurance, crystalline behavior studies, and things like that. And we are looking at least 4 or 5 experiments of this class have already been shortlisted: biological instruments, material science instruments, optical fibers making, etc., on board Gaganyaan program. We put all the data coming from science missions in one repository called Space Science Data Center, which is created at Ahmedabad and at the ISTRAC, Indian Space Science Data Center. It's a data repository where we collect all the data coming from all science missions in a standard universal format. Because across the globe, there is a data sharing format. Principles are there between NASA, JAXA, ISA. All science missions follow this principle. And all scientists talk to each other. And we also deposit our data in this form, in this data center, and make it shared between scientists of the world over. And they share their data to us. but there are some lock-in periods. And we advise you, those who are interested in making use of science data and do research, please communicate with ISRO, and we'll be happy to share this data wherever through an evaluation process, of course. And we look at how space research in India has to continue. See, the exploration missions like Chandrayaan 3, etc., doesn't happen just like that. It happens over a period of long discussions, debate, justification, money. It goes through rigor of looking at it. And though you say it's a low-cost mission, don't think that you are just quickly making another Chandrayaan 4. So much of work is required to make any mission. So we go through a large segment of the society, scientific community into discussion mode. And many people put forth the proposals of these are the things which you are interested to do. ISRO assimilate all of this, create a new project, go to government, seek funding. It's a long drawn process. What we need in this country is that scientists who have an interest to work in space should come together, participate in this, send proposals to us. And if you get good proposals, it will be very good for us to justify any new mission in the future. Without scientists available to analyze this data and make science out of it, there is no point in doing missions of this nature. It's a very complex, high investment missions. And what is needed is a capacity in our universities, scientific establishment to make sense out of the whole data. And I will advise today in INSA that we need large number of people to make use of the data and make publications, research and findings, which couldn't be done otherwise. And from anywhere you won't get this beautiful data, because if you do it yourself, you get the best of the data. And we also need people who are capable of building instruments. And it's not easy. Building high technology instruments is very difficult. It takes a lot of patience of engineering work, sensor work, data analytic work, microelectronics design and development. It's a very difficult process. And we need high caliber engineers to do that as well. So it's a work of scientists who understand the data and then make sense out of it. Instrument builders who work on instruments, then of course satellite builders who build the satellite, and finally the rocket people to put it there and operate and land. It's a synergetic work of large number of people. So I wish you become one of them in the chain of events. Thank you so much.
So thanks a lot from the bottom of our heart for such an engaging and outstanding lecture. I request everyone to please give a big round of applause for Shri Somanath. Now it is the time for the interactive session with questions and answers. If anyone has any question, kindly raise your hands. We would be able to take only 3 to 4 questions due to constraints of time. I request Dr. V.M. Tiwari sir to kindly conduct this session.
So I think we must again thank Professor Somanath and also congratulate for such a wonderful talk. I'm sure I told that there may be hundreds of questions, but as desired, we will start with a few questions from young people and then move to the other press and media, because they may get a chance with Professor Somanath other time as well, but the young students might not. So one question, please raise your hand, and yeah, last one. Quick, be specific and.
Good evening, sir. Firstly, I'd like to thank you for providing this opportunity. Sir, I would like to know about Gaganyaan mission and when will we go to space and send our astronauts?
I'm not here to talk about schedules.
So anyone who would like to learn more about science or the engineering aspects? Yeah.
Good evening, sir. Sir, I'm an undergraduate student and I'm in 3rd year, and we would love to have an opportunity to learn with ISRO to gain practical experience. But there are no such programs which we can access those things. Can you tell us more about
You are doing what?
Sir,
No.
aerospace and avionics.
In undergraduate or postgraduate?
Undergraduate, sir. Integrated program.
So, yeah, in fact, undergraduate, we don't give any opportunity for it. If you are a postgraduate or a research fellow, of course, there is a possibility. Because undergraduates are in lakhs in this country, and it's very difficult for them to give any opportunity on specific training program. So maybe you can connect with one of the center where to your native place where you can do the final year project or seminar type of work. We allow 3 months of internships, not really internship doing project work. That is limited only. But if you are a master's person, if you want to work on your final year project, it is possible. We also encourage to work with us. If you're a doctoral person, there are doctoral possibilities internally as research within ISRO. There are many areas in science domain we give possibilities of working with us. You can also get in for internships, short-term internship on domains if you are in the master's or PhD level. Otherwise, in undergraduate, we are not in a position to give because of the large number of people cannot be allowed within the organization in that level, because it's hampered with our day-to-day work.
Hi, sir. Sir, you talked about launching of space satellites. Sir, how do you address and overcome the issue of space debris?
Yeah, it's not an issue for me alone. It's an issue for the entire world. You know, the number of satellites launched last year itself is 3,000, and number of debris are increasing. So there are no ground rules today. The only rule that is available is the good behavior. So there are certain good behavior described for all space operators. One of them is that you declare everything that you are launching that we should do. Second is, once life is over, try to deorbit. So that we try to do. If it is a low Earth orbit, bring it back to Earth. And if it is a geo-orbit, take it to the graveyard orbit. Then make sure that if rocket parts doesn't contain pressure and or fuels, etc., so that it cannot explode and create large debris. Then you continue to cooperate with people who are observing the satellite. There are agencies across the world who looks at every satellite, every object which is bigger than 10 centimeter and catalog it and monitor its trajectory. And this is called the observation data which comes out. There are many agencies. There is one in Europe, then one in US, Russia, and China is slowly developing. And India is also developing this capability over a period of time. And after that, you are trying to do conjunction analysis. When all this data comes, 20,000 objects and its trajectories are known. And which one will hit what? You have to do every day this calculation. So we created a huge program in which this data will be put in, and every day you find out conjunction analysis, and some of them may come very close. Alert the satellite, that particular satellite, and make it move a little bit here and there so that it doesn't collide with each other. So we do all of this on a continuous basis. So over the years, I believe there will be better guidelines will come, so that you should not allow any dead satellite to be left there. It has to be necessarily taken down by an active mechanism. So people look at active debris removal as a major topic, and that is slowly picking up. Okay.
Hello. Yeah. So towards the end of your presentation, I saw that you mentioned the Indian space station. If you can elaborate a little more on what is the idea, is it is going to be an international achievement which will be led by India or which will be part of? It's something that we will be building for the world, and what kind of science goals are we looking at for the Indian space station?
I'm not in a position to explain it at this moment because it is an idea which we have to expand on it, and it's a policy matter with the government. So let me work on it.
One from the balcony. Yeah.
Hey, don't fall down. Huh?
Yeah. So young one, listen.
You are leaning too
Yeah.
much. Yeah, you are. Huh? See, the entire battery which is flying in satellite and launch vehicle is actually built by ISRO. It is done in-house. Okay. All the lithium cells which you are flying in rockets, satellites are built by us. The chemistry is internally done. The manufacturing is also done. Okay. So we work on various batteries. We have been working on nickel hydride battery, silver zinc batteries, that time onwards, silver zinc, nickel hydride, then the lithium ion. Now we are now reached solid state lithium ion. And we are now working on sodium based batteries. Already prototypes have come out. You are researching on it, but we have already built it. So, but sodium, of course, it doesn't have energy density as much as the lithium. So it actually bulky, not good for space. It may be more suitable for terrestrial applications. High temperature also, we have some programs working on cells, but high temperature is not a must in space. As you understand, the space is actually low temperature. And you have to keep heating it. You have to put heaters on outside, and all our batteries are provided heaters outside to keep it warm. So otherwise, it actually loses its ability. So with respect to the space-based system, the lithium-ion cell seems to be one of the best. Today, we have satellites which work with 15 years lithium-ion cells unserviced. You can understand that once you launch 15 years, there is no service, no maintenance. It works. Only thing is it will degrade over a period of time because every battery has a charge retention capability comes down. Number of cycles of charging is also limited. But we are able to make space grade lithium-ion cells which works for 15 years. It's working very well. I think it is good enough for us for space program. Right now we are on par with the world class. But we are not selling it to anybody, only doing for our own work.
So
But we have transferred technology to BHEL recently. BHEL will be making it for public use.
So we have last question with the senior young.
No. When you said young people can ask question, I was going to ask it. We are young, they are younger.
Yeah.
Okay. So don't ever, mistake people for being old. But anyway, so a very scientific question, so when you look at the moon surface,
Yeah.
and there's total vacuum there.
Yeah.
So how does water hang on there? It would just,
Water cannot hang on there.
right?
See, because of the pressure being lower, it would have already sublimated and gone if any surface water is there. What happens is if you take a sand particles here, it actually contains water. Hydroxyl molecules are trapped inside.
Yeah, I get it.
So any silicon compound contains hydroxyl molecules trapped inside. So the material traps hydroxyl molecules, and it can also trap water. Because if you take a sand, it contains water. Even if you heat it, it will not escape. It still will contain strongly absorbed. So that way it is present. And we expect that the temperature just below the surface, we have measured the temperature. The surface temperature is 20 degree. Just 10 centimeter below, it has reached minus 30, 40 degree. Just 10 centimeter below. That means if you go a little deeper, the temperature would have gone so deep, so low that it would have already crystalline and it will not sublimate. So it will be able to remain as solid water deeper inside. That's understanding.
I think we need to close it. So, sorry, we don't have time. See, I think one thing what we have learned today, which is very much always debated, is what drives science, whether technology drives science or science drives the technology. And the answer we got from your presentation today and with your interaction, sir, that without technology, it's very difficult to get the data, which is the mother of the all scientific inventions. So we thank you, and we'll have formal vote.
Thank you. Thank you, sir. Now I request ED INSA, Dr. Brajesh Pandey, to please deliver his vote of thanks.
Good afternoon, sir. Ladies and gentlemen, I would like to extend my heartfelt thanks to our guest, an eminent personality in space research, Shri Somanath ji, Chairman ISRO, for his spectacular talk in our first INSA Distinguished Public Lecture. We are thankful, whole INSA family is thankful to you for giving us time and inaugurating this lecture series. I would like to thank our President, Professor Astrosat Sharma, for continuously encouraging us for this particular series of lecture. I would like to thank Dr. V.M. Tiwari for his support. This whole lecture series or this particular lecture is started because of your consent and continuously we have followed for 1 month. So I would like to convey my thanks to your secretary, Sodaji, because I have called her so many times, and my office called her so many times, and presently she has given the time. So thanks her. I would like to express my thanks to esteemed audience, those who have make it happen and great success. And thanks to all INSA technical staff and other people, our security staff, and everybody to making this particular evening a great success. Thank you, sir.
Thank you. Thank you, everyone, for your gracious presence in INSA Auditorium. Now we end today's event here. Thank you. Thanks to you all.